All right, everybody, we're back again for some more logs. Today we're going to talk about common logarithms. And all a common log means are just logs that have a base of 10. So we use them in a lot of applications, but we're going to talk a little bit about how this works and what their inverses look like, and kind of just the basic idea of what a common log might be used for. So logs with base of 10. So on your calculator, what you can do is look for the key that just says log. So the key on your calculator actually looks like this, but what it means, what you have to assume, is it's a log with a base 10. They just never write the 10. It's kind of like having a variable x just standing there, and they assume everybody knows that that's to the first power, or there's a 1 out front as a coefficient. So log base 10, that's called a common logarithm because it's commonly found in things all over the place. We'll talk about some applications of that. So inverse of a common log, opposite operation. Remember, logs are inverses of exponentials. So if it's log base 10, that means its inverse then would be 10 to the x. And if you look on your graphing calculator, sure enough, right above the log key is the 10 to the x key. So that's the inverse of the opposite operation. That's how your calculator is set up. The inverses are also called anti-log. So anti meaning inverse. So that's just kind of another phrase or word for inverse. So when we talk about anti something, it means the opposite. So in calculus, for an example, next year you'll talk about derivatives and then antiderivatives. So it just means inverse or opposite. So 10 to the power. Okay, so just so you can see how this works, I have things written in exponential form. So powers of 10. So common logs are base 10 numbers. So all those powers of 10 are written out in exponential form. Well, we can write them all in log form as well. So I'm going to rewrite this first one, 10 to the third equals 1,000, in log form. So kind of doing our b to the p equals n deal here. So base being raised to a power equals a number. We're going to rewrite that as a log. So it'd be log base b. Well, it's a base 10 log. Again, we don't normally write that though, but that's what that means. So I'm not going to put the 10 there, but just know that that's assumed. So log base 10, log, of the number, which would be the 1,000, is equal to, so what that means is 10 to what power gives you 1,000? Well, 3. So base 10 log 1,000 is 10 to the third. So kind of following that same pattern, then the log base 10 of 100 is asking the question, 10 to what power gives you 100? Well, 2, and on down the line. So log base 10 of 10, so common log of 10, well, 10 to what power is 10? 1. Now it gets a little bit interesting. Log base 10 of 1. So 10 to what power would give you a 1? Well, look at your exponent. It has to be 0. Follow the pattern too. Look what it's doing on the other side. 3, 2, 1, 0. Can kind of predict where we're going to go here. So log base 10 of 0.1. Now, sometimes it's hard for people to think of this, but it's also the same as, if you'd rather, call that a 1/10. Might be a little bit easier for you to see what's happening. How do you get a 1/10? Well, the 10's in the denominator, so that would be a negative exponent to the negative first power. So 10 to what power would give you 1/10? Got to be a negative 1. Look at the pattern on the other side too. 3, 2, 1, 0, negative 1 makes sense. So the log base 10 of 1/100th. Think of how you say this. 1/100th. Same as this, if that's easier for you to look at it that way, would be 10 to the negative second. And then the log base 10 of 1,000th, 1 over 1,000, again, same as 0.001, would be to the negative 3 power, 1 over 10 cubed. And you can keep going. That's just to give you some benchmarks. So you have kind of a basic idea of what log numbers look like. So log of 10, that's 1. 10 to what power gives me 10, and you can go from either direction. All right, let's talk about anti-logs then, just so you can recognize what these look like. Anti, remember, means inverse. So the anti-log of 3 means the same thing then as 10 to the third power. That's what an anti-log is. So it's an inverse of a log. So 10 to the third, yeah, that's 1,000. So anti means inverse. Anti-log of negative 1.5. That means 10 to the negative 1.5 power. So negative exponents, those are going to be small numbers because it's 1 over. That's the same thing as doing 1 over 10 to the 1.5 power. So if you do that on your calculator, you should get about 300ths, or 0.03. So when you see the word anti or that prefix, that just means 10 to the inverse. Okay, let's try another one. Evaluate the expression. So when we start dealing with log statements, I just want you to have an idea of what's reasonable. So when you see something like this, it's asking the question, again, log base 10, so you have to assume that the 10's there. So it's really the same as saying this. I know it's not written there, but that's what you're assuming. What I do for these, again, is think of that as being equal to something. Set it equal to a value so you can think of it as an exponential, so you can think of it in terms of its inverse. So if I rewrite this as an exponential, what that question is really asking is 10 to what power gives you 70 or 752.6. Well, that sure isn't a whole number answer, but I bet we can guesstimate. Let's go back to our powers of 10 chart. 10 to the third is 1,000. 10 to the second is 100. So our answer for what we're doing has to be somewhere between a power of 2 and a power of 3, because our number, 700 and whatever, is between 100 and 1,000. Probably a little bit closer to 1,000. Okay, so how can we figure out what that is? Well, you can literally type into your calculator, use your log button, log of 752.6. So you just type it in, and you should get what that power would be. And I believe it comes out to be 2 point, go out a few places here. So if you raise 10 to that power, so 10 to the, as many digits as you can get here, you should get pretty darn close to 752.6. That's what that number means. So you're finding the exponent. Remember, logs are exponents. 10 to what power gives me that? So you can just type it in your calculator, but understand what that means. So what that green statement is saying, that is what log of 752.6 would mean. All right, so let's do an application. I know some of you in chemistry or AP Chem have done this when we talk about the pH of something, measuring how acidic or how basic something is. I know in your textbooks for chemistry, the formula is a little bit different, so I want to give you a moment to think for a moment. What is the formula for pH? And some of you are saying to your screen right now, well, Mrs. Zabel, pH is the negative log of the hydrogen concentration. Right. Hopefully you remember, Miss Benson, Mr. Zabel will be proud of you. In our textbook, they say it a little bit differently. They say it like this. I just want you to see the difference. They say this, that it's the log of 1 over the hydrogen concentration. I want to see if you can figure out if those are actually the same thing. So if I rewrite 1 over H with a negative exponent, that would be log of H to the negative first, right? And then where else, using the product property, can we put that -1? Well, that comes right out front, and then you get the same as the other formula. So negative log of the hydrogen concentration. So you can use either one. Either of those green formulas work just fine. It just depends on what you're accustomed to. So if you're given the hydrogen concentration, you can find the pH. Or if you're given the pH, you can find the hydrogen concentration. All right, so let's take a look. I'll try to use the one that you're more familiar with, because I know that's what people are doing. So if this is the hydrogen concentration, and we want to find the pH, it would be negative log base 10, common log, of 7.94 times 10 to the -9th. Great application of when people use a common log. So 10 to what power gives you that for an answer. And so just try that in your calculator, type it in, and see what your pH should be. And I got 8.1. Make sure you type them in and try them. Well, now we can go the other way as well. So it says, technicians here said the water supply has a pH of 6.7. So they're figuring out that their pH is 6.7. So that's what they calculated to be. I'm going to use the other formula again. So negative log of the hydrogen concentration. So if they want you to solve for what the hydrogen concentration is, we kind of need to work backwards to figure this out. So really what you're saying is 10 to what power? But the first thing that I'm going to do is go ahead and divide by that negative so I can get that on the other side. So log of H. So remember, this is base 10. So to solve this statement, I'm going to rewrite it as an exponential so I can see what that looks like. So 10 to the -6.7 would have to be that hydrogen concentration. And so if you do that, just type that in. I got 1.9953 times 10 to the -7th. So we can solve either direction. So we can rewrite that as an exponential. It's a log statement. Use its inverse or the opposite operation to solve. All right, so hydrogen is our concentration. pH is a great example. We'll do other things. Like if you've heard of the Richter scale for measuring the magnitude of a of an earthquake. That is another scale that's a log scale where they just look at the magnitude being that exponent, what power 10 is raised to. So the difference between, say, a magnitude 5 earthquake and a 6, it's actually 10 times more intense because it's the exponent. It's the difference between 10 to the 5th and 10 to the 6th. Okay, so let's do some solving stuff. So really the big application that we use common logs for is solving equations that we can't solve so easily with some of the other things that we've used. So in the last couple sections, we were able to solve because we could make the bases the same. 2 to what power gives me 8? 3. Great, that works really well. But what if the bases can't be made the same? Let's look at the one on the left. 4 to the x equals 13. Well, 4 to a whole number power is never going to be 13. So how can we use logs, the opposite operation, to solve? So I'm going to bring you back to algebra. You always use the opposite operation, right? So I'm just going to write this really quick. So if you have multiplication in an equation, how do you solve for x? Well, you divide, right? That's the opposite operation. Same thing for logs or in exponentials. We use the opposite. So this is an exponential. What we're going to do is take the log on both sides. And maybe you remember this algebraic approach from last year. So if I take the log on both sides, what that allows me to do is use log properties. So I'm using the inverse. So log base 10 on both sides. So where else can this x go? Well, out front. So that would be x times the log of 4 equals the log of 13. Remember, those are both just numbers. 10 to what power gives me 4? 10 to what power gives me 13? And then solve for x. Divide by log of 4. So you're able to actually type this all in one step on your calculator. Log of 13 divided by log of 4. Notice that's log of the number, divided by log of the base. So I'm doing kind of that same process over and over again. So for this one, I got about 1.85. Now, if you wanted to check your answer and see if you were accurate, you'd have to go back then and see if that would work. So if I did 4 to the 1.85 power, try that, you should get pretty darn close to 13. But why isn't it actually 13? Well, you think? That's because we rounded, right? So 1.85 is a rounded answer, so it'll be pretty close, but not perfect. All right, so a similar idea for the next one. I want to kind of talk to you about what happens if it's not just an x up there. There's no whole number that's going to give me that answer, so I'm going to go ahead and use the opposite operation, the inverse operation, and take the log on both sides, which allows me, once again, to bring down that exponent. But notice the exponent is an expression. So 3 times x times the log of 6 equals the log of 81. Remember, log of 6, log of 81, just numbers. How do you solve for x? Well, not only do you have to divide by the log of 6 on each side, you have to divide by that coefficient of 3 as well. So if you look at the exponent, if there's other things in the power with the x, you're going to have to undo that too. So if there's a times in there, you're going to have to divide. If it was a divide up there, you're going to have to times. If it was add something, you're going to have to subtract. You still have to do the opposite operations there. And when you do that on your calculator, be careful. Make sure you divide by all of that. So use parentheses when you type it in there. I got 0.82. So again, you could plug 0.82 in for x and make sure that that seems reasonable. So we're looking for those values. So logs are a great tool to use to solve. So once you start doing a few of these, notice again, you had log of the number, 81, divided by log of the base. And you kind of keep doing the same thing over and over again, and you realize, gosh, that's always the same. And that's called the change of base formula, which basically says, get it? Basically, funny. All right, that you can take the log of the number divided by log of the base anytime. So if you have a situation where you're trying to calculate log base b of a number, it's always equal to log of the number divided by log of the base. Every single time. That's the same sort of thing you do. And where that comes from is if you take your b raised to some power equals a number deal, if you go through and solve like we just did in the other ones, take the log on both sides, you're going to end up taking the same division every time. So I'll follow through that process. So say I take log of both sides of this. So log of each side. That means I can bring down my exponent. So I was solving this exponential situation here. So x times the log of b equals the log of n. To get the x by itself, you divide by the log of b. And we're back to what we had there on the top. So it's always, every single time you have an exponential like this, it's always going to be, to get that power, log of the number divided by log of the base. So that's what we call the change of base formula. So if you have either this statement right here, log base b of n, or this statement right here. I guess I'll let this equal to x so you have the same idea. In either of those statements, so in log form or in exponential form, b to the x equals n or log base b of n, both of them you're going to solve by taking common log of the number divided by common log of the base. If you know that, it makes things like this really easy. It says find the log base 9 of 1043. Well, you don't have a base 9 key on your calculator, right? But if we can convert this using change of base to common logs, it's really easy to do. Take log of the number, which is 1043, divided by log of the base, which is log of 9. So just type it on your calculator once. So just go ahead and do common log divided by common log. I got 3.2. Where does this come from? Well, I'm going to write it as an equation, because for some people I think that process idea really helps. Set it equal to something. Rewrite it as an exponential. So 9 to what power gives me 1043? Okay, well great, that's not a whole number answer. I'll have to go through and solve. How would you solve it? Well, you do exactly what we did in those last couple examples. You take the common log on both sides. You'd be bringing down the x, and you'd be dividing. So you can see why you don't necessarily want to go through and do this every single time if you know that that's what's going to happen every single time. So it's a shortcut for all of that arithmetic that you're doing. Log of the number divided by log of the base. Okay, so for the next one, log base 6 of 72. That means 6 to what power gives you 72? That's what that statement is saying. 6 to what power gives me 72? Well, you could guesstimate. 6 squared is 36. 6 cubed is bigger than that. It's probably in between then 2 and 3. Well, just do log of the number, 72, divided by log of the base, log of 6. And we get about, I got about 2 point, I guess. I went out 4 places, so it'd be about 2.4. So when we're looking at those values, it makes it a little bit easier to see. So change of base formula is super handy. Okay, let's finish up with a couple last ideas about using log properties that we talked about before with common logs now, with base 10 logs. All those properties work the same. We'll do a couple property things in one last solving. So take a look at this one. We almost have equality properties. So we have 2 logs that have the same base, because notice there's nothing there on either of them, so it means base 10. But we can't solve with equality if we have the 1/4 out there. So where else can that 1/4 go? Well, it could be the exponent. So we'd have log base 10 of x to the 4th equals log base 10 of 15. We've got equality, so we can set what's inside equal. So x to the 1/4 power must be the same as 15. Now you just have to solve for x, so we need to use our algebra skills. 1/4 power, remember, is the same as 4th root, if that's an easier way for you to look at it. How do you undo having a 4th root? Well, how do you undo a square root? Square. So how do you undo a 4th root? Raise it to the 4th. So the easiest way for me to show that would just be to do this. So raise it to the 4th power. So just 15 to the 4th. And that puts us at 5625, so 50,000. So they get pretty big again, these exponentials. So solving logs, we can use very much the same idea. Okay, so now how is this different? What I want you to take a look at is to really see how much more complicated it gets when this equation is a little bit more challenging. So in this case, it's more challenging because look up in the exponents. You have variables on both sides, so that makes it a little bit more work for you, but you still have to do inverses. There's no way you can really solve this because it's not a whole number answer. So I'm going to go ahead and take log on both sides. So we're going to talk this one through here. And that brings, or gives me the ability, I guess, to bring down those exponents, because otherwise they're really hard to solve for if they're in the exponent. When they're out front, they're just a regular variable. Did you notice what I put around the x minus 1? Hope so. That's really important to make sure we get that entire thing multiplied by log of 5. Now remember, log of 5 and log of 2 are just numbers. So right now what a lot of people will do is they'll go ahead and just figure those out in your calculator and put them in as a decimal. So log of 5, when you put that in your calculator, I got 0.70, so I'm going to go out to 2 places. I guess I'll put it out front then. And log of 2, I got 0.30. So distribute and solve for x. So those are just numbers. Go ahead and put them in that way. Get your x's on one side, numbers on the other. So I guess I'll subtract this. So I get negative 0.70 equals negative 0.40x divide by negative 0.40. And my x value, that x1 that it would have to be, I got about 1.75, I think, with those values. It's going to be a little bit off again because we rounded. If you want more accuracy, obviously we can go to more places. But if I wanted to check and make sure that that answer is true, I can plug 1.75 back in for each of those. So 5 to the 1.75 minus 1 should be pretty close to 2 to the 1.75 power. See that that's the same. Or graphically, if you wanted to use your graphing calculator, you could graph those two equations and see where they meet. So if you look at your graphing calculator approach to this, just seeing what does this mean? What are we talking about? The first one is 5 raised to the x minus 1. The second one is 2 raised to the x. I'm going to go ahead and just do a zoom 6 to make sure I have a regular graph. What this really means is we're looking to see where these two graphs are equal, where they cross. Okay, well, we can kind of see where that point is. It looks like it's about there, right? Which for my x value is supposed to be like 1.75, which is pretty reasonable from the picture. You could trace on your graph and just see approximately where it crosses. Or under the calculate menu, you can actually do intersect, which is kind of nice. It's this number 5. So you can say, okay, what's your first curve? Yep, it's that 5 to the x thing. What's your second curve? Yep, it's the 2 to the x thing. And then your guess, get it kind of close. So go ahead and get it close to where you think it is. Press enter, and we can get a pretty good approximation. So they had 1.756. So graphically, that's what it means. When these two things intersect, that's the place we're looking for. So it's just another, I guess, another approach, another way to look at solving. It's just where are those two things the same? We're going to skip the graphing for right now. We're going to hang on to that for another point. So we'll talk about that later. So the assignment that we're going to be looking at, though, is working with logs, anti-logs, solving equations with logs. And so that's on page 730, 11.5. You can see everything on here. And we're going to do more applications. So the rest of the week, we're going to dive into where else can we see these logs in real-life applications. So happy log solving, and we'll be back for another installment soon.